Alright there, welcome back to Think Tank Online Learning. In this video, I'm going to look on bending stresses of beams. So we're given a problem. A simply supported beam shown in the diagram has circular cross-sectional area of diameter 100 millimeters. A load F equals 3 kilonewtons is applied at its mid-span. The material from which the beam is made of is steel, of which the elasticity is 110 giganewtons per square meter. Determine the maximum bending stress in the beam. So the support A is a pin and this one is a roller. So we're just going to apply principle of moments and just find the stress. Okay, so the formula that we're going to use to calculate the stress, M times Y max divided by I.
So mx is the bending moment at any section, and I is the moment of inertia, and y is the distance from the neutral axis to the fiber on which the stress acts, and y, you can treat y as the center of gravity.
Okay, so to solve our problem, let's just start by drawing a free body diagram. So this is the free body diagram that I'm going to draw, and I'm going to remove support. So I'm going to have reaction at A, going to have reaction at B, RB, and to still have our force, which is going to be F. So what we're going to do, I'm going to write the equation of static equilibrium. Okay, so what I'm going to do, I'm going to resolve along the Y. So the sum of the forces should be equal to 0 since it is static. So Fy should give me 0, and I'm going to take the upward as the positive. Okay, so what forces do I have? I'm going to have RA here, which is going to be positive because it's acting upward. So I'm going to say RA, and F is opposing, so it's going to be negative F. And I'm going to have plus RB, and this should give me 0. That means I can say RA plus RB. So this is RB, and that should give me F. That is going to be equal to 0. And the other thing that I'm going to do, I'm going to take moments about the point. I can choose A or I can choose B. Okay, so I'm going to take moments about the point. Let me just take point A. And I'm going to treat the counter, the clockwise, as positive. You can do what you want. Nothing doesn't matter. So if we take moments about this point, since RA is going to pass through the point, it's going to be 0. So I'm going to look at F. So F is at a distance, and we can agree this one is going to be the center because we're told in the question that F is applied at its mid-span. So this is 4.2. So the distance here, we can agree that this distance is 2.1 and the distance here is 2.1. So what I'm going to do, I'm going to have F. So you can see when you apply a force F here, this beam is going to move. It's going to rotate in the clockwise direction. So I'm going to have positive F times the distance, and you can agree that the distance is 2.1 here. If you are not familiar with moments, just look on my video in the description under the playlist Mechanical Engineering. Okay, then on B, you can see B is trying to lift the beam, so it's going to be opposite. So it's going to be negative RB, but times the distance from which you're taking the moment, so it's going to be point A. So it's going to be times 4.2, and that should give us 0. And you can see that RB times 4.2, that's going to give us F. We know F is 3 kilonewtons, and I'm going to multiply that by 2.1. And after that, we're going to make RB, the formula. So that means I'm going to say 3 times 2.1 divided by 4.2, and all answers and kilonewtons. And I think if we do that, we can find our B as 1.5 kilonewtons. So since B is 1.5 kilonewtons, from equation number 1, that RA plus RB should give us F. So if RA is going to be F minus RB, that means it's going to be 3 kilonewtons minus 1.5 kilonewtons, and that is going to give us 1.5 kilonewtons. So that means we have our force at the reaction, our reaction force. Okay, we have RA, which is going to be equal to RB, which is going to be equal to 1.5 kilonewtons. We have everything right now. So now what we're going to do, I'm going to look for mx, the moment at the point. So what I'm going to do, I'm going to take just a section either on the right of this diagram or on the left. So I'm going to take, you have to take it before the force or after the force. So let me just put here, let me just choose, you can even choose Z. So this is the section that we're going to take. I'm going to take Z, and I'm going to say the distance from here to Z, I'm going to call it X. So let me just write it here. I'm going to have RA right here, reaction at A, and I'm going to have a distance. We have said the distance from here to here, we said it's x, and let me just indicate here by saying this is the section ZZ. Okay, so what is going to happen? I'm going to say the moment at this point, let me just call it mx, and I'm going to take counterclockwise as positive. So now I'm going to apply the moment equation. So the sum of the moments at x at this point, let me just call the section, I'm going to call it ZZ, should give me 0. Okay, so what is going to happen to A? A is going to make this rotate in the clockwise direction, so it's going to be negative RA times the distance from this point, which is x, plus the moment at this point, which is mx, and that should give me 0. And from here, I can agree that mx is equal to RA times x, and RA, we have our RA here, is 1.5 kilonewtons, and x. So since the maximum bending stress is going to occur at the center, you can agree that it's going to be 2.1, and you can see that mx is going to be 3.15 kilonewtons. Now what do we need? We need y max and also need the moment of inertia. So if we look at our question, it says that the cross section of the beam is a circle. So if it is a circle, it is going to have a center right here. Okay, so what I'm going to do, because I don't want to work too much, I'm going to take this point as my reference axis. And since the diameter of this circle is 100, that means the distance from here is going to be 50 millimeters. So I've said I want to look at y max as the center of gravity. So you can see here the distance from here to here is going to be equal to 50 millimeters. So I can write my y as 50 millimeters. Okay, and if you want, you can just apply that y max is going to be the area times the distance from the reference axis, which is going to be pi radius squared divided by the area of the total region, which is going to be pi, also say that the area, which is pi r squared, and I'm going to multiply that by the coordinate of y, by the distance from the reference point to y. So this is supposed to be y, and I'm going to divide it by the area, which is going to be pi radius squared. So you can see from here the distance from the reference point to this end is going to be 50 divided by 1, since pi r squared in pi r squared is going to be 1. But since it's just a circle, know that the center of gravity is going to be the center. So y max is 50 millimeters. Now let's look at the moment of inertia of a circle. So the moment of inertia of a circle, pi r squared over 4 here, and I'm going to multiply that by the radius. So the radius is going to be 50, but I'm going to change it to meters. So it's going to be 50 times 10 to the power 3 meters, right? And I'm going to put 4 here, and I'm going to divide this by 4. Okay, and if we do that, we're going to see that our I is going to be pi over 640,000, and here it's going to be m to the power 4. So the maximum stress is going to be mx, which is 3.15 times 10 to the power 3, to change kilonewtons to newtons. I'm going to multiply that by y max, which is 50 times 10 to the power negative 3, change that to meters, and I'm going to divide it by m by I. It's going to be pi over 640,000 m to the power 4. So the other thing that you have to know here is that the units for mx is going to be m. So I'm going to just put times m here. Since I said find mx, we multiplied the force times the distance. Okay, and if we do this, we're going to get our units for stress, which is going to be newtons over meter squared. So it's going to be 32.086 mega Pascal. So thank you for watching. Don't forget to subscribe. On the next question, we're going to look at the deflection and of rotation for this problem.